This is deeply disappointing. It appears that we may have to wait even longer for the Moon mission as ongoing testing continues to uncover additional issues with the SLS. As a result, the SLS will need to return to the VAB for further inspection and work. So, what happens next? Alongside the challenges facing the SLS, NASA has also had to acknowledge the difficult reality surrounding the Boeing Starliner program. In contrast, SpaceX continues to demonstrate its capabilities through successful Dragon crew missions, Falcon booster landings overseas, and the achievements of new records in rocket reuse. Arguably the most significant milestone NASA has conducted in recent days was the second overall wet dress rehearsal of the SLS or Space Launch System, and notably the second attempt within the same month. After adjustments were made following the first incomplete test, expectations were elevated. The February 19 attempt demonstrated meaningful progress. Launch controllers conducted two terminal countdown simulations reaching 2's 29 seconds and 2's 33 seconds. These milestones confirmed that automated sequencing, tank pressurization logic, and launch commit criteria were functioning within expected parameters. Just as importantly, the core stage completed full cryogenic loading of both liquid hydrogen and liquid oxygen. Given hydrogen's volatility and tendency to leak due to its small molecular size, achieving stable fueling conditions marked clear improvement. The previously observed hydrogen leak showed improvement following seal replacements, and the Orion spacecraft remained thermally and structurally stable throughout operations. Collectively, these results strengthened confidence in the vehicle's readiness for a potential March launch window. However, a new issue emerged after fueling operations concluded. The anomaly involved helium flow within the INTRAM cryogenic propulsion stage, the upper stage responsible for performing the trans-lunar injection burn. The ICPS uses high-press helium stored in composite overwrap tanks to purge engine systems and maintain proper tank pressurization during engine operations. While the helium system functioned normally during the rehearsal, engineers encountered difficulty when attempting to recharge it during post-test servicing. Helium could not be successfully reintroduced into the vehicle. Helium presents unique engineering challenges. As an inert gas with extremely small atomic size, it can migrate through microscopic imperfections in seals or valves. Diagnosing flow interruptions is complex because leakage paths may only appear under specific pressure differentials. The concern here is not merely the interruption itself, but the system's failure to behave repeatably during standard servicing procedures. NASA Administrator Jared Isaacman indicated that potential fault locations include a final filter between ground equipment and the vehicle, a quick disconnect umbilical interface, or an onboard check valve. A similar check valve issue occurred during Artemis 1, though corrective actions were implemented for Artemis 2. The recurrence of comparable symptoms, even if the root cause differs, increases scrutiny before flight. Because resolving these potential faults requires direct access to hardware interfaces and internal components, the vehicle must return to the VAB or Vehicle Assembly Building. Such troubleshooting cannot be fully performed at the launchpad where access is limited. Rollback operations are complex. The mobile launcher must be secured, umbilical stemmated, and the vehicle transported back to the VAB at controlled speeds. Inside, technicians can conduct inspections, testing, and replacement of suspect hardware. The schedule implications are significant. A rollback introduces repair time and re-verification time. After corrective action, the helium system must be retested under cryogenic conditions to confirm resolution. Depending on the intervention required, additional integrated testing may be necessary before flight certification. Under even an efficient timeline, an early March launch becomes unlikely. Lunar missions are governed by orbital mechanics. Trans-lunar injection opportunities depend on precise Earth-Moon alignment to ensure proper arrival conditions and safe return trajectories. Missing one window typically shifts the next viable opportunity by several weeks. In this case, the next practical window moves into April, assuming remediation proceeds smoothly and no additional issues arise. Whether an April launch remains achievable depends on how quickly the root cause is isolated, corrected, and validated through repeat testing. What remains clear is that stable helium and hydrogen management must be conclusively demonstrated before the mission proceeds. The resolution of this issue will determine not only the timing of the next launch attempt, but also the system's readiness for sustained crewed lunar operations. If recent setbacks surrounding Artemis 2 have raised concern, the situation involving Boeing Starliner carries even broader implications for NASA's human spaceflight architecture. Nearly 2 years after its most recent crewed flight test, the program now faces a structural reassessment that extends beyond a single anomaly. Following an extended investigation, NASA conducted a formal press conference outlining the technical findings and programmatic consequences of the Starliner incident. On February 19, NASA Administrator Jared Isaacman released a detailed summary describing the investigative process, identified root causes, and future constraints on the vehicle's operational role. The review classified the Starliner failure as Category A under NASA's safety framework. Within the A's risk taxonomy, Category A denotes the highest severity level, conditions that could lead to loss of crew or loss of vehicle. While the outcome did not result in catastrophe, the classification reflects the potential consequences had contingencies fail. Such designation automatically triggers heightened scrutiny, procedural reform, and re-evaluation of certification pathways. Technically, the incident centered on two primary propulsion-related issues: a helium leak within the pressurization system and degradation in multiple reaction control thrusters. Helium plays a critical role in maintaining propellant tank pressure and ensuring stable feed conditions for maneuvering engines. Any loss of pressurization margin can compromise thrust consistency and vehicle controllability. Concurrently, the underperformance of attitude control thrusters reduced redundancy and a system designed to tolerate isolated failures. When redundancy margins erode, crew risk tolerance narrows sharply. As a precaution, the crew flight test astronauts were returned to Earth aboard Crew Dragon, underscoring the operational resilience provided by NASA's dual-provider commercial crew structure. However, that redundancy was precisely the strategic objective of the program to prevent reliance on a single transportation system. With Starliner now suspended from further crewed flights pending full propulsion requalification and corrective action verification, NASA effectively returns to a single operational crew transport vehicle. The agency has stated clearly that Starliner will not carry astronauts again until technical causes are fully understood, corrective measures are implemented, and the propulsion system is comprehensively requalified. In the interim, discussions indicate the spacecraft may transition to cargo-only missions, though that represents a significant departure from its original mandate as a crew transport vehicle. The broader implications are substantial. NASA invested approximately $4.5 billion into the Starliner program under the commercial crew framework structured as a fixed-price contract intended to stimulate competitive innovation while reducing long-term operational cost. Boeing has additionally absorbed financial losses due to schedule delays and remediation efforts. Beyond direct cost, the decade-long development timeline reflects opportunity cost, delayed operational redundancy, constrained scheduling flexibility, and increased reliance on a single partner for human access to low Earth orbit. Competitive dynamics further complicate the outlook. SpaceX has demonstrated consistent operational cadence with Crew Dragon, achieving routine ISS rotations and establishing a reliability record that reinforces institutional confidence. Meanwhile, cargo providers such as Seniors and Dreamchaser continue to develop or operate within the resupply market, though neither currently fills the crew transport role. Whether Boeing can restore confidence will depend not on rhetoric, but on demonstrable engineering correction and sustained operational reliability. And now let's turn to SpaceX and a sequence of milestones that reinforce its operational dominance. After minor weather delays, SpaceX and NASA successfully launched Crew 12 on the morning of the 13th of February with docking at the ISS completed the following afternoon Eastern Time. The mission delivered 4 NASA astronauts to orbit, stabilizing station staffing after Crew 11 had been forced to depart early due to a medical emergency. With the new crew aboard, handover procedures were executed efficiently and routine ISS operations resumed. The broader implication is continuity. As the ISS approaches the latter phase of its service life, reliability and crew rotation is no longer just a logistical necessity. It's foundational to maintaining research cadence, international commitments, and long-term transition planning. Crew 12 demonstrated once again that SpaceX's human spaceflight architecture centered on the Dragon spacecraft and Falcon 9 has matured into a predictable, repeatable system. For observers concerned about access to orbit, this mission served as reassurance. The pipeline remained secure. SpaceX did not pause there. On February 19 at 8:41 p.m. Eastern, a Falcon 9 lifted off from Cape Canaveral Space Force Station carrying 29 Starlink broadband satellites. While Starlink launches have become routine, the landing profile drew particular attention. Booster B-1077 completed its 26th flight with a successful touchdown on the drone ship. Just read the instructions in the Exuma Sound region of the Bahamas. This marked the resumption of landings in Bahamian waters following an environmental review that temporarily paused operations after an earlier attempt. Clearance from the Civil Aviation Authority of the Bahamas reopened that corridor, signaling not only regulatory approval, but also the geographic expansion of SpaceX's recovery infrastructure. Reusability, once a technical experiment, now operates across international boundaries. 2 days later at 10:47 p.m. Eastern on the 21st, another Falcon 9 launched from SLC-40 at Cape Canaveral. The focal point this time was booster B-1067 as it landed aboard the drone ship a shortfall of gravitas, marking its 33rd successful recovery. That figure is not incremental, it's historic. No orbital-class booster has flown and landed that many times within the SpaceX fleet and across the global launch industry. B-1067 stands as a benchmark for reuse.